As promised, we will now focus on first-order differential equations. And in particular, we'll not just consider single equations, but we'll consider full systems of equations. So that means there will be actually several functions that we have, for here x1 up to xn, which we conveniently can write in this vector notation as vector x of t. And there is basically now n equations for these n different functions, and all different functions can appear in all the different equations. So that's what we call the system of equations. And you can write that in general such that the first derivative with respect to t of the vector x of t equals to some vector valued function which depends in turn on x of t again. And the initial condition again becomes, like in vector form, x of t0 equals vector x0. Now, this is the most general form of a system of first-order differential equations. As I said before, we'll actually focus on linear systems of equations. But for now, let's just briefly take this most general form, because we can also actually learn something nice for these systems of first-order differential equations. What we can learn from them is that they actually give rise to a quite intuitive understanding of how they work. Now, what we have here in this, I just write this equation again here. Now, if we look here on the left-hand side, we have x dot. So that is basically a velocity. So the derivative of x with respect to t, if t is the time, that gives me a velocity. And basically what we can say is that, well, this is the velocity of some particle in our system. The right-hand side that we have here, what we see here is that this is a so-called vector field, and this defines a velocity for every point x that enters here in the argument. So what we can actually do is we can draw this vector field. I made a sketch down here. So what we have is that for every point in space, and I can only draw a two-dimensional space, so that's what I did here. For every point in space, we have a given velocity, and I'm basically drawing this vector field here. So how we can imagine the solution to come about is that let's start from some initial condition, which is the point x that I draw here. And imagine there's a little car sitting here at this point. And what this equation here does, it tells the little car which velocity should you have at a given point. And by demanding that this little car has a certain velocity at a given point, you can uniquely steer it through this space. So what you actually have is that at every point, so here this velocity was given, so it will go in that direction. And if we just follow these points, we'll see that it actually follows a certain curve, a certain path. And this is the solution to the differential equation. Now, what I described here in a graphical way, you can actually also make a very nice, mathematical theorem, which we'll not cover in this course, the so-called Picard-Lindelöf theorem, which gives certain guarantees about that solutions always exist and that solutions are unique, that you basically can go forward and go backward in time, and you know where it came from, basically. Now, this theorem is something that you, strictly speaking, need to prove some of the things that I will just state in the next few slides. So I will not prove everything that I will show you, but essentially the proof more or less boils down to what I showed you here graphically. But then, of course, you have to just formulate it in a much more mathematical way. But now let's actually turn to the linear systems of first-order differential equations that I promised you in the beginning. So a linear system of first-order differential equations is an equation of the form where the derivative of the x vector equals to a matrix A, which might depend on the time t, times the vector x itself. So you see that this is indeed the form of a linear system of equations where the x1 to xn are variables. So in this expression here, A is a n by n matrix, and x is an n-dimensional vector. Now, what is important to realize is what it means that this is a linear system of equations, because that will make things much easier for us. And in particular, what linearity means is that if we have two solutions, x of t and y of t, then also the linear combination, so a times x of t plus b times y of t, is a solution. And this is very useful because, as you will see, it allows us to find specific solutions and then combine them together to find any arbitrary solution that we want. Now, what you also can actually already see here is why these linear differential equations are very useful for, or very important in quantum mechanics, because what we have in quantum mechanics is, or what basically follows from the fact that quantum mechanics is described by linear differential equations, is that we have the superposition principle in quantum mechanics, which essentially means that what is just written here, that if you have two different solutions, then you can also make a superposition and still get a valid quantum mechanical solution. So what we can now actually do is we can actually formulate a theorem that for a system like this, there exists a general solution, namely that for an n by n system that I just defined on the previous page, I can show that the general solution to that problem is x of t, which is given by a coefficient c1 times phi vector phi 1 of t plus and so on up to cn times vector phi n of t, where we have phi 1 of t up to phi n of t n different functions which form the basis of the solution space. And one can show that for these linear differential equations of first order, when I have an n by n system, there is always n linearly independent solutions that form the basis of the solution space. So we'll come back to that several times during our discussion, but it's important to always remember that there are n independent solutions. What one can do furthermore, one can actually show that these phi 1 of t to phi n of t are a basis if and only if the determinant of the matrix that I get by just combining all those column vectors together into a matrix, that if this determinant is not equals to 0. Now, this maybe it's not even surprising for you because you know at a given time t, but if I just fix my time t, then my point x here is just some point in n-dimensional vector space, and we know that an n-dimensional vector space has n independent basis vectors. So this is basically the condition for those basis vectors to be linearly independent. So why is this equation here actually useful? Well, it's especially useful because if we find n different solutions, we can use it to check if there are a basis. And what's actually nice, and this goes beyond what we know from linear vector spaces, is a property of these first order differential equations, is that we only need to show this for a single time t. So for only one time t, we need to if we can show that for one time t, those form a linear basis of the n-dimensional vector space, then it will hold for all times t. This is a consequence of this Picard-Lindelof theorem that I was telling you before. And it basically tells you, when your little car starts and you go ahead, then there's a unique solution at every point. So this is a nice and useful equation, and we'll be using it to show that we actually found a basis of our solution in the following. So what I showed you so far is a so-called homogeneous system. So I didn't say that name before. So this is of this form. We call a form like this a homogeneous system of equations. There's also the inhomogeneous system of equations where we additionally add a vector B of t. And well, what we now want to look at is we want to make a connection of this inhomogeneous system back to the homogeneous system, because it actually turns out that although this looks much more complicated than the other one, because now it's, you have this term here, actually it's only more complicated by one solution in a sense. And you will see immediately what I mean by that. Now, what we need to do is we need to make an observation. And for this observation, let's assume that we already found two solutions, psi1 of t and psi2 of t, of the inhomogeneous system. I forgot the vector errors here. Now, if we have two solutions of the inhomogeneous system, now let us look at the difference between these two solutions. And in particular, we can look at psi1 dot of t minus psi2 dot of t, which is, the same as saying ddt of the difference between those two. Now, if we write it out, we can use the inhomogeneous differential equation here to write the expression for psi1 and psi2 dot. And when we do that, take the difference, what we actually notice is that this vector b of t will drop out because that's the same for both solutions. So that what we end up with is a of t psi1 of t minus a of t psi2 of t. And well, then we can just write this as a of t times, in brackets, psi1 of t minus psi2 of t. But if we now look at this, what we realize is that the difference between the two solutions of the inhomogeneous system is actually a solution of the homogeneous system. So whenever I take the difference between two solutions of the inhomogeneous system, I get a solution of the homogeneous system. Or in other words, the solutions of the inhomogeneous system differ only by a solution of the homogeneous system. Now this allows us immediately to write down the general solution. Namely that x of t is given by some solution to the inhomogeneous system plus, well, a solution of the homogeneous system. But for that, we know that we can write this with our basis vectors phi1 up to phi n. So plus c1 phi1 of t plus cn times phi n of t. And well, this really follows from what we were just saying before, that the different solutions to the inhomogeneous system can only differ by the solution of the homogeneous system. So we see that we only need to find one solution for the inhomogeneous system. And we need the n solutions of the homogeneous system. And in this sense, the inhomogeneous system is one solution more difficult because now we need n plus 1 solutions in total. So whenever you have an inhomogeneous system, what you actually always do is you first try to solve the homogeneous system, and then you only go ahead for finding the solution to the inhomogeneous system. And it actually turns again out there is a nice trick of how you can do that. And for that, indeed, you need the solutions of the homogeneous system. So what we do is we make a little ansatz. We make an ansatz and say x of t equals to c1 of t times phi 1 of t plus cn of t times phi n of t and all the other terms in between. And if you look at this briefly, you would say, oh, hold on, isn't that the solution of the homogeneous system? And well, it isn't, because for the homogeneous system, the c's are just constants. So the only time dependence is in the basis vectors phi n of t. So here we make a more general ansatz. So it could reduce to the solution of the homogeneous system, but it can also be more general. What we now want to do is we want to, because the whole thing here is just a handful to write down, we just make some small definitions to have a more compact notation. And what we first do is we define a vector c of t, formed by all these coefficients that we have here. And we make an n by n matrix phi of t out of all the vectors phi 1 to phi n of t, again, by just stacking all those column vectors together to form an n by n matrix. And then it's actually easy to see that in doing that, we can write x of t as a product of a vector times a matrix, because if we do that, then we get c1 times phi 1 of t, c2 times phi 2 of t, up to cn times phi n of t. So it's just a nice and compact notation that will make life for us easier. So what we now do is we will now put this ansatz into the differential equation. And differential equations start with x dot of t. So we want to put this ansatz in there, so we need to compute d dt of phi t c of t. And we have a product here, so we need to use the product rule. And we get phi dot of t c of t plus phi of t c dot of t. So we get two terms because we have a product. And if we now plug in the right-hand side of the differential equation, what we get is a of t times phi of t c vector of t. So this is just a of t times x of t plus b of t. But what we also see now is that because we have phi dot of t equals to a times phi of t, so you know that the columns of phi of t are the solutions to the homogeneous equation. So let me be a little more precise here. This is actually a of t phi of t. For that reason, these two terms here drop out, because these are just these terms, these are just these times the vector c. So this drops out, so that's nice. With this simplification, our equation now simplifies to phi of t times c vector dot of t equals to b of t. And then we can solve for c dot of t. And we get c dot of t equals to phi of t to the minus 1, so the matrix inverse times b of t. And the point is that we can always take this matrix inverse because, well, we actually showed that the phi's are only a basis if the determinant of that vector, of this matrix consisting of these vectors, is not equals to 0, so that, which means it's invertible. So that's nice, so we can always do that. And then, of course, we can also easily integrate this equation because, this is just the first order differential equations again. So we just get c of t equals to the integral of phi of t to the minus 1 times b of t dt. So, if we now plug this expression for c of t again in our ansatz, which was, as shown here, this matrix phi of t times c of t, we find that one solution to the inhomogeneous problem is given by phi of t times integral phi of t minus b of t dt. So just notice, here is phi of t times phi of t to the minus 1. Those, of course, don't cancel because there's the integral in between. But this is a very compact expression for finding a solution of the inhomogeneous equation. Now, it is, of course, when you want to do the calculation, it's a little bit tedious because you need the matrix inverse and all of these kind of things. So it's not a lot of fun to do this calculation for a linear system of equations explicitly. But it's good to know that it exists. And for example, it can be useful also when you want to apply it to just a single equation that is of this inhomogeneous kind. And that's what we'll show in the next example. So there we can do this still very explicitly. So here I just repeat what we were just deriving before, the general expression for finding the solution of the inhomogeneous equation. So I apply this now to an example where I use a differential equation we had before, namely x dot equals to lambda x, where we already found the solution to the homogeneous problem before, plus alpha now. So well, what we know is that, well, it's a 1-by-1 equation, you know, so it's just a single solution. We found it before, and we had phi of t equals to e to the lambda t. So this is the basis of our solution. And then the general solution was c times e to the lambda t. Now, let's just plug this into our equation that we have here, right? So we first do the integral, and that is phi times, so this phi to the minus 1, which is e to the minus lambda t times b vector, which is now, in this case, it's just a single number, alpha dt, and this we can easily integrate to give us minus alpha divided by lambda e to the minus lambda t. And with that, we now then easily find the solution of the inhomogeneous system, which is given by phi of t, which is e to the lambda t, times the integral that we just computed, which is minus alpha divided by lambda e to the minus lambda t. And this is just minus alpha divided by lambda. So with that, we see that the general solution is given as x of t equals c times e to the lambda t minus alpha divided by lambda.